The concept, the vision of space solar power is in fact to go to space in the vicinity of the Earth to harvest there the nearly limitless and continuous energy of the sun, to transform it and to deliver it safely, affordably, and nearly continuously to locations across the world. As an example, 3 different solar power satellites located above the designated spots on the Earth, one of them above Africa, one of them near Indonesia, and the third one in the Pacific off the coast of South America. Those 3 satellites could deliver power to a particular market addressing a total of about 90% of humanity. So with a mere 3 satellites, one could in principle address 90% of humanity as a market. It's not to say that you would deliver power to all of the 90% all of the time, but rather that from one of those 3 satellites, you could deliver power to a receiver on the ground. And if it can be done affordably, and it can be done reliably, and it can be done in scale, then this would fundamentally change energy for the Earth. So I'd like to talk to you in 3 parts about the case for space solar power. First, I'd like to highlight what the drivers are for new energy on the Earth. And the next few minutes has almost nothing to do with space. It has a great deal to do with us, because we are all inhabitants of this world. So, what is driving the demand for new energy sources? Certainly, the first and foremost driver is the ongoing increase in the global population and the surging demand for a better quality of life by peoples across the world. Second, there is a fundamental issue with the use of fossil fuels, which is driving, in my opinion and the opinion of many, climate change. I know this is a controversial topic. It is not inherent in the argument for space solar power, but it is an important part of the policy framework within which space solar power will be brought forward. And lastly, there is the Hubbard Curve and what it means for non-renewable resources. That's on the Earth. In addition, in space, there are significant drivers for opportunities for new power, including both existing markets and ambitious future goals and missions. So, firstly, and most importantly, population and economic growth. As of about noon today, there were 7,233,852,000 individuals on this planet, on the way to an additional 4 billion by the end of this century. Those people, 7,233,000,000 and so on, consumed last year, these are approximate numbers, a total amount of energy equivalent to 120,000 kilowatt hours. So a substantial number of terawatt hours. And this is energy from all sources. Per capita, that works out to be 17,000 kilowatt hours per year per person. But there's a trick in that. And the trick in that is that 2 or 3 billion people out of the 7 billion plus use little or no amount of that energy. And in fact, we in the United States, as individuals per capita, including all sources, transportation, industry, heating and cooling, everything, use on the order of 80 or 90,000 kilowatt hours per year per person, when the world average is on the order of a quarter of that or less. And of the developed countries, including Japan, which only uses about half of our number, the US number, and other countries such as in the Middle East where they use more than our number, you take out the developed countries and it means that there are billions of people who have almost no energy other than that which they can glean from sticks or bits of waste or what have you. By the end of this century, it's estimated that the population of the world will be on the order of 11 billion, or maybe not. It could be that there will be a great economic and societal collapse. And if that's true, then the population will be about 5 or 6 billion. However, if current trends continue and there is not an economic collapse, and it is not possible to get population growth under control, the real number will be more like 15 billion. And so the 11 billion person number is kind of a middle ground. With regard to the energy used by those 11 billion people 90 years from now, there are some options. Option A says the status quo stays the way it is. The number of people who have energy stays about the same and grows proportionately. The number of people who have nothing stays the same and grows proportionately, and so on. In that case, the world will need on the order of 180,000 billion kilowatt hours in 2100. Option B, some people stay poor, but more people have a better quality of life, in which case it works out to be about 480,000 billion kilowatt hours. And option C is everybody becomes successful and everybody has a pretty good quality of life, in which case it needs to be more than, I'm not even going to try to say that number, a stupendously large amount of energy. And what this means is that during the next decades, there is a stupendous demand for new energy sources of some kind. So whenever anybody says, if it stays at this kind of level, this is what's going to happen, it's not going to stay at this kind of level. People who are currently living in poverty don't want to continue to live in poverty. They want a better quality of life. And as a consequence, option A turns out to be 80,000 million kilowatt hours more. Option B is 360,000 million kilowatt hours more. And option C is 800,000 million kilowatt hours more per year. And if you don't believe that this is going to drive the energy marketplace, look at the numbers for China over the past 20 years. And what you see is a rocket going up. And this reflects the 7 to 10% per year economic growth in China, none of which happens without energy. And similar numbers, a little bit smaller slope, similar numbers in India. And you cannot tell yourself that all of those other hundreds of millions of people in other parts of the world don't want it too. Where is it going to come from? Well, the key point is that in the U.S., about 80% of this energy that we use today comes from fossil fuels. Coal, oil, natural gas. In China, it's more like 90%. If we try to stay on this track while the total consumption of energy in the world quadruples or increases by 9-fold over the next 90 years, the amount of fossil fuels that were consumed would be stupendously huge, which in and of itself is not morally or economically a bad thing. However, there are reasons why this is problematic. First and foremost, there is the fact that any given field of fossil fuels is finite. A gentleman by the name of Hubbard, a statistician, first observed in the 1950s that for all these existing fields of gas and oil in particular, that they have a life cycle, and it looks a lot like a Gaussian curve. They are found, they're developed, they start to produce, they peak, and they slowly decline. And if you add all of those numbers up over all of the fields in all of a region like Pennsylvania, you find that there's a way to predict when the oil in that particular area, region, will peak and will begin to decline. It doesn't say you ever run out of oil. It just says that the amount of oil produced in a given year peaks and begins to decline. Now, what happens when a resource which is in demand goes into decline, but the demand doesn't decline? The answer is markets work, prices go up. New technologies come in as substitutes for the old technology, which is becoming less and less affordable given the economics of how energy is used in the society. First point. Second point, this chart is actually from Dr. Peter Glazer's first paper on space solar power, and it shows a version of the Hubbard Curve in which he thought about this issue, and what he said was, well, looking at the forecast for how energy is being used in the mid-1960s, looking forward based on Hubbard's kind of statistical analysis, what we see is that around the year 2100, global energy consumption will peak at about 50,000 billion kilowatt hours per year. Well, as you'll remember from the previous chart, here we are in 2014, we're already at 120. So we are some 50 years after Peter Glazer's paper, we are consuming not quite, but almost 3 times more energy per year than was anticipated at 50 years ago to be the global peak. The reason it's happening is not U.S. consumption, it's that the rest of the world is starting to use a lot of energy. So in this forecast that he looked at, real energy consumption started around the time of the Industrial Revolution and before that, and it would peak around 2100, and around 3000, all these fossil fuels would be depleted, and sometime during that 1500 years, we had to solve the problem. Well, if you go back to the previous diagram, what you see is if in fact the rate of consumption is 3 times higher now than this forecast, and as it's on its way to being 4 times higher than that or 9 times higher than that, we are by the end of this century going to consume essentially, not all, because you never consume all of a consumable resources, but enough so that oil, gas, and coal are very likely to peak. If they peak, it doesn't mean we run out, it just means prices will go up. Another issue with business as usual through the end of this century, through the quadrupling or the octupling of the amount of energy that we need per year, and that's carbon in the atmosphere. So this simply diagrams the historical data on CO2 emissions and accumulations in the atmosphere over the last 100 years plus, several hundred years, and looks to the future if in fact the amount of energy consumed does in fact quadruple, which was sort of the middle of the 3 forecasts. And what it suggests is that CO2 accumulations will, in the context of business as usual and quadrupling the amount of fossil fuels consumed per year, setting aside for the moment of whether or not they run out, CO2 concentrations will go absolutely through the sky, pun intended. And if you didn't see it the other day, last Friday, there was an article in Science saying that it's now confirmed by 2100, the western sheet in Antarctica, the ice sheet, will collapse, will slide into the ocean, and sea levels will rise by 8 feet. And by the end of the following century, by another 5 or 6 feet. So this got a fair amount of press, and it's just happening. So again, I'm not saying that this is a central part of the argument for space solar power, because I know it's controversial in the US, but I am saying that the fact that there is a broad scientific consensus about this issue, the fact that it's getting worse, not better, over the years, suggests that there will be a very advantageous policy environment for the introduction of new renewable energy sources. Over the next decades, there is a vast demand for energy of all sorts, energy globally, and energy that is affordable or maybe even not so affordable, because the prices of the energy that we've been using are likely to increase. So, if space solar power were a good idea, it's been around for 50 years, why aren't we already doing it? I'd like to speak about 3 eras for space solar power. So the first era, that of the 1970s, was the era of the monoliths. So in that era, the architectural concepts for space solar power were vast versions of the satellites that were known of the day. So this particular one is a stupendously large conventional 3-axis stabilized platform, which depended upon a very large shuttle-like looking 2-stage to orbit reusable launch vehicle. And I should mention that in this design concept, the wing of the lower stage of the 2-stage to orbit is as large as the Space Shuttle orbiter. The factory in the center where these platforms were going to be developed is a half a mile tall and 4 miles long. And so it's a truly vast concept, a vast structural concept, and then the receivers on the ground. Now, what was especially interesting about the monoliths in the concepts was also that the project concept was an equally large monolith. So the vision in 1979, 1980 was that these huge platforms, a single system, each one weighing on the order of 50 to 60,000 ton, would be developed in a single large satellite project, as would the vehicles, as would the in-space assembly, as would everything. And it would be done like Apollo. There would be several decision points, Phase A, Phase B, in the normal NASA systems engineering kind of parlance. And the whole thing would be done as a single large project to develop these single large systems. So I call this the era of the monoliths. And what we saw in this era was that the costs involved were equally stupendous, ultimately estimated to be on the order of $1 trillion to get to the first commercial kilowatt hour. This is one of the reasons why the era of the monoliths died as it did rather suddenly, right around 1980, 1981. So, the second era, the era of partially modular space solar power. So in the 1990s, there were a series of concepts, one of them from Professor Kaya in Japan, and others from NASA's studies of the day, 1995 to 2001, which introduced increasing levels of modularity into SSP systems concepts, principally with an eye towards getting rid of the requirement for the extremely large in-space construction facilities and the stupendously large two-stage-to-orbit reusable launch vehicle. Now, even though those things were disposed of, nevertheless, there were still some really substantial parts of the system architecture that were still monoliths. So it was only partially modular, not fully modular. So for example, there was a concept known as the sun tower, individual solar collection parts of the system, but it was still a single power backbone taking the voltage down to the transmitter at the base. In addition, in this era, it was politically essential to demonstrate every step in any kind of a plan to do space solar power was going to have benefits for future NASA programs. And the result was a very different kind of roadmap forward, a very different programmatic strategy than let's go do a $1 trillion version of the Apollo project. And instead, what it was a series of steps in which you'd have first 4 or 5, 6 years to do a 100 kilowatt demo, and then 4 or 5 or 6 years to do a 1 megawatt demo, and so on. And these things would sort of step up in scale and complexity, and after 30 or 40 years, you would reach a solar power satellite that would deliver energy to the Earth, and in the meantime, you'd develop a lot of systems that were useful to NASA programs and potentially DoD programs. Now, this era also came to an end in around 2000, 2003, but the large-scale effort and the idea of NASA working on this failed in large measure because NASA wanted to work on other things. So the argument, this is going to be really good for NASA. Let's do a megawatt class power system and you can use it for all of these great purposes, failed utterly because NASA at the time wanted to work on space nuclear power. Or NASA had no real need for a megawatt. It just needed, 50 kilowatts, and it didn't really want to get it. So this all went away also. And the costs were really not as low as they needed to be because it was still essential that it be a large-scale government program. We have now reached what I am calling the era of hypermodular satellite architectures. This architectural approach is epitomized in the sandwich module concept that Professor Kaya has been working on for several years, and also by the new system concept which I am promoting, which is called SPS Alpha, a solar-powered satellite via arbitrarily large phased array. This approach is derived from nature. It is biomimetic. And so if you think about how nature accomplishes things, some of the most successful species over the last several 100 million years have been these superorganisms like ants or colonies of bees or termites. And in this case, you have a large number of very simple intellects, i.e. insect class intellects, which cooperate to accomplish quite ambitious and sophisticated ends. Sometimes humans are capable of cooperating in this way, although often for means or for objectives that are not really for the good of the species. In this case, a large group of them forming a pattern as they're hurtling towards the Earth. Other times you see this kind of cooperation out on the football field, where the objective is to move a little ball a couple of 100 yards one way or the other. In SPS Alpha, the approach to space solar power is now completely decomposed, and there are no large-scale monolithic pieces left at all. What you have is some 8 building blocks, rather like Legos, which are mass-produced and which are used in assemblies to form a variety of different space solar power systems. So you've got the fundamental building block, which is this ring that looks like a hexagon. You've got some connections. Those things come together to make structures. You've got others, which include the hex bus, the connectors, and some large solar sails to make reflectors, basically make heliostats, and so on and so on. It's a lengthy story to talk about exactly how all of this works. The key point being that a single solar power satellite is no longer going to be comprised of 4 or 5 unique systems, each one thousands of tons in mass. Rather, it's going to be comprised of 1 million small sats. Each one is 1 to 5 kilograms in mass, and they cooperate just like the swarm of ants or the swarm of bees to accomplish the functions of the space solar power program. Why is that a good thing? Why is this a really powerful new paradigm that explains the question I posed a moment ago? If space solar power is such a good idea, and if demand is so great, how come nobody has done it? This is the roadmap for SPS Alpha, which is in the report that I did for NIAC and is in the NASA Innovative Advanced Concepts program and also in my new book. And the fundamental message is that as you march from the lower left, design studies and preliminary research, to the upper right, where you have operational solar power satellites, you march not through a series of completely redesigned and re-engineered projects at larger and larger scales. Rather, you march through multiple generations of assembling the Legos, the building blocks, into larger and larger platforms. At the same time that that is going on, these building blocks can be individually evolved, adding new. If you've ever looked at the evolution over the last 12 years of USB drives, you know that they started out a number of years ago at a gigabyte, and then they're at 2 or 4, and then they're at 8, and then they're at 16. The other day I bought one that was at 32. But the USB drive into which you put the port into which you put the drive has changed very, very little. It's gone through, I think, 2 generations. Similarly, a lot of the other key interfaces with our wireless and networked economy, like TCP/IP or HTML, those things have stayed relatively constant over generation over generation over generation. I won't ask the question because it's obvious. How many computers are there in the room? Probably more computers than there are humans. How many times in the last 6 months have you had an upgrade pushed to one of your devices? So within the standard, with the framework of a good set of standards and interfaces, rapid innovation and ongoing evolutionary change in the technologies to improve the system happen elegantly in a competitive marketplace. And that is the central idea of SPS Alpha programmatically. So in this example, several of the design reference missions are illustrated. DRM-0 would be an initial demonstration, just 6 or 8 of these modules, test them on the ground, fly them quickly to space. This could be done for millions of dollars and months. The individual piece parts range in size from 1 kilogram up to an average of about 15. The biggest one is a solar sail, and it's only massive because it's got a lot of thin film material to provide the solar reflection. None of the piece parts are particularly economically challenging or difficult in terms of schedule or facilities. Similarly, DRM-1 is the next size up, DRM-2 is the next size up, and these are interesting not just because they are on the path to the vision of space solar power, but because by the time you get to DRM-2, you have now got a communications satellite bus which is 100 times more powerful than the best satellite bus on the market and costs half the price. 10 times more effective revenue, but 20 times more cost effectiveness. And this, as an avenue to transforming how current markets in space work, represents a stupendously attractive economic opportunity. It is enabled, simply enough, by the learning curve and by the concept of mass production of these modular system elements. Not to say it's easy, but to say that it is much easier to sort out mass production and network systems and manufacture 1 million once you work it out than it is to make, for example, a single computer that would provide the IT and communications need of 1 million people. In this case, at the far left, you have the early DRMs, just a few units, and when you get to the right, you have a DRM-5. It's a large solar power satellite. It involves many hundreds of thousands of modular elements, and in principle, the price approaches in dollars per kilogram consumer electronics today. If this is true, and it's easy to test, takes months, not decades, the number of applications becomes amazing. As an example, in human space exploration, the cost today for a kilowatt hour on the International Space Station is on the order of $50 a kilowatt hour. The same kind of price tag applies to almost all of the advanced energy systems that have ever been studied, and I led lots of the studies when I was at NASA headquarters, for example, for lunar power, or for Mars power, or for space nuclear power, $50 to $100 per kilowatt hour. Now, none of the ambitious things that we all hope to see are ever going to happen if it costs 1,000 times more per kilowatt hour than to do the same kind of activity here on Earth. and it doesn't have to. It is possible to break this by not doing it that way. Similarly, robotic exploration missions. If you look at the scope and scale of the kinds of robotics, the power systems, the propulsion systems, the scale of these solar reflectors, they're like solar sails. Every university professor in the world could, submit a proposal and for a couple of $1 million, send a solar sail powered little small sat out to his or her favorite small body. Space settlement, space development. How much are we really going to do in the extraction and exploitation of the resources of the solar system at $50 a kilowatt hour until we have ubiquitous, constant, affordable, and reliable transportation across the inner solar system? All of those things become possible if you solve the issues associated with SPS alpha. Energy for terrestrial markets, we've talked about that. Certainly there are tremendous potential applications in energy security, civil emissions. The point being, each of these markets, these mission opportunities, can be quantified over the coming 10 to 20 years. And if you do that and you run the numbers and you do the business case for the roadmap, you get some really appealing numbers. For example, this looks over the next 6 years at DRM 0, 1, and 2, looking in particular at communication satellite market applications for these kinds of systems. Then extending that same set of curves out to DRM 3, which is the first substantial in-space system that could deliver power in the megawatts to Earth, and looking out, as we like to do as visionaries, over the coming century and holding it conservatively to only 100 gigawatts, 100,000 megawatts of space solar power for markets on Earth. Again, and at this point, the industry associated with modular systems, SPS alpha, is on the scale of the automotive industry in its heyday. There are literally 1 million people working in manufacturing systems for space, and the business, after taking out the costs, is making on the order of $60 billion a year net. If these numbers are correct, there's a tremendous opportunity involved in space solar power, and it's a commercial opportunity. So, how would space solar power really affect the future? It appears that the hypermodular approach, because of the low barrier to entry and because of what it would mean to have these kinds of systems and energy power for space, would enable a clear, affordable, and practical path to large-scale solar power from space. Within 10 to 15 years, space solar power would be the largest space industry in space and in history. Within a few decades, space solar power delivered to markets on Earth would be benefiting people across the globe. Because in space, space solar power would mean megawatts across the inner solar system for pennies a kilowatt hour, it would fundamentally transform everything we do in space. So the emergence of affordable and profitable space solar power would have far-reaching impacts on the future of our activities in space and the future of humanity on Earth. Leaving just one question. If it's so easy to pursue this and determine whether or not this vision is in fact realizable, why wouldn't we do it? Thank you very much.